Okay, good morning. So let us move on to the next chapter. Yes, this is based on my experiences for some students a little bit subtle because there are many things that you need to consider. They are not hard at all, but we have different algorithms that you shouldn't mix them up with each other. So we learn the notion of the derivative from abstract point of view, even though we have already learned some applications of the derivatives, one in pure geometry to find an equation for the tangent line, and then one was how to find the instantaneous velocity of a moving particle if we know the position of the particle as a function of time. But now we mainly want to focus on applications of the derivatives in the realm of mathematics for the time being. So you see that, so you already know about the graphs of functions so far, but if you want to look closer into the graph of a function, it is not that easy task at all. Yes, even if, for example, you have Geogebra and then you draw the graph of a function using Geogebra, you have a limited display in front of you. You cannot be able to see all parts of the graph, yes, because might be many graphs actually continues to infinities from directions. So you have a limited view of what you see of the graph of the function, yes. So if you see, for example, I was more or less when I was doing Math 2C, for example, assume that you want to draw the graph of this function y equals x squared. I want you to understand, this is a really hard problem. It's not a simple task, because by a graph of a function, it means that I need to find all possible pairs of x and y so that they satisfy this equation, yes? But this is not possible because there are infinitely many of them. I can put x equals to 1, I get y 1, I can put x equals to square root of 2, I get y equals to 2, and then you can imagine infinitely many possibilities, and it is clear that I will not be able to feed in all possible values for x to find the corresponding y. And in principle, this I want you to understand. When you draw what is the meaning of the graph of a function, it means that this is the set of all possible pairs x and y so that these two numbers satisfy the equation of the function. Yes? And then, for example, whenever I find a pair, 1 and 1 is one of those pairs, yes? Because if I replace x with 1, the answer becomes 1 squared, which is 1, and I have given you y equals to 1. So it means that, in principle, I just assume that this is a display, this should be highlighted. Yes? But by the way, this is not just a dot because this is not dimensionless. There are infinitely many other numbers very, very close to 1. I cannot distinct them. In principle, I have to consider all of them, which is not possible. And then, for example, if I put 2, I get 4. Then I will go and find this one, yes? And then 4. Okay, but I want you to understand that this cannot go forever. I just highlight a point here, I highlight a point here, I put 0, y becomes 0, I put -1, y becomes again 1, and then I put -2, it becomes 4. I just want you to understand that even though you know that the graph is this, is because someone like your teacher already told you this is the graph. But I cannot just highlight 4 points and say that this is your graph, because I hope that you agree with me that there is no guarantee that the graph doesn't act like that. Yes, why not? This is another graph. Of course, you can rule this possibility out. You can say that, okay, I will take 0.5, I put 0.5 here, I get 0.24, which is here, then I convince that, no, this is wrong. Okay, but then another person comes in, how do you know that this is wrong? I mean that this can continue forever. So this is why I really want you to understand that drawing the graph of a function, even though technically is easy to understand, but practically it might be very hard. Yes? Because we don't know how the function acts. Unless we really have a powerful tool in our hand to predict the behavior of the graph of the function. Yes? For example, how do you know, by the way, I can ask GeoGebra to draw that, and then you have a limited display, and in this limited display you see this. But in principle, you should not be convinced that this is the graph, yes? Because how do you know that this will not return back? You can say that way, I zoom in 2 or 3 times and I see this is not happening. But still, how do you know that if you zoom in 100 times, this will not appear, yes? Do you understand what I mean? Because it doesn't matter how big display you have and how many times you zoom in, this is always finite, yes? And then how many points are there for you? Infinitely many. You cannot discover the properties of infinitely many points by just a finite number of steps. Yes? At least I want you to understand where the practical problem is. Yes? Is that clear? Okay. So we need to have some kind of tools in our hands to make everyone convinced that no, even though I have a limited display, but this strange behavior will not appear regardless of how many times I zoom in. So I can be sure that this behavior for this function does not appear. So I just want you to know, it doesn't matter how computational tools you have in your hand, you cannot confirm that this cannot happen forever. But if you have mathematics in your hand, you can predict such a behavior for this function will not appear, regardless of how many times you want to spend time on it. This will not appear. So these kinds of predictions needs a very systematic approach to the problem. Yes? And that is coming from the derivative. And if you remember, we studied some part of these things in chapter 1 without even mentioning the derivative. Now I want to recap a little bit about that and come back and to make it more systematic. Okay? I really want you to learn this because everything you learn here you will need it in Math 4 as well. And this is a little bit lengthy chapter, and then we will see what happens. Okay, so now let me ask you something. If I give you the graph something like that, okay, I just intuitively, okay, I'm asking you, of course, how many points are there? Let me put for the time being an arrow. I will. It means that this will continue forever, for example, from that side. But it is not very clear. Forever means it returns back or not. But don't be distracted by those kind of questions. If you want to draw the graph of this function, of course there are infinitely many points. But can you guess which points probably are more important when it comes to drawing the graph? Yes? I don't know, I'm just asking this intuitively, because if you can understand it, then I can save a little bit of breath for myself not to explain it so much. Yes, Abdul Manan?
Local maximum, maximum.
Oh, okay, so you are saying these bombs and troughs, yes, here. So might be these are important, because if you give me these, at least I can be relieved that around that point, this graph will not return back. And if you give me this point, then you can just actually be convinced that at least very close to this point, I will not expect that the graph is going to return down. Yeah? And then if I know all these local max points, do you remember? Local mean. Do you remember what was the meaning of local max? The adjective local and global. Of course, sometimes instead of global, people call absolute, yes? Do you remember what was that? So here you see it is locally a maximum point, but what does it mean? It means that if you consider the points in the vicinity of this point, in the neighborhood of that, the graph of the points very close to this are all lower in height than this point. So this means that this is locally maximum compared to its localhood, it is higher. But, for example, you can see that this point is still lower than that point. Yes? So I cannot say that this is a global maximum. Because if you look to this graph globally, all of it, it is somehow lower than some points. So it's not globally a maximum, but it is locally a maximum. Yes? And then this is the same thing here. Of course, in this picture it seems that, but if it continues forever like that, this is a local minimum without being a global minimum. Yes? And then I can have a lot of actually max and min points. Yes? So for example, if you give GeoGebra to draw the graph of the sine function, so you will get probably something like this oscillating. Yes? And then you see that I have infinitely many local max points and infinitely many local min points. Yes? Is that understandable? So, I want you to look at this problem right intuitively, that hopefully, if I ask you, I want to give you a finitely many points so that you have a better chance to draw qualitatively. The graph of the function, which one do you prefer that I give you to? You will tell me probably these local extreme points. Yes? Because if I know that this is a local minimum point, I know that around this point the graph should look like that. But of course, it might be very wider, it might be very narrow. But I mean that because we are humans, for a robot probably understanding the difference between tape, it needs a very big algorithm to design which one is for. But for humans, you see that we have a feeling that these are of the same type of shapes. One of them is wider, one of them is sharper. But at least you see that around the mean point, the graph looks like that. And around the max point, the graph will look somehow like this, yes? Around that point. Yes? Okay. So now, and the other point is that the questions that I want to address are very trivial if you have the graph. It's just a primary school question. If I ask you, can you recognize what is the local max point? I think if the people listen to me, they probably immediately show this one to me. And when I say what is the local mean, they can show this one. The point is that I don't be careful. The logic is the other way around. In chapter 1, we had the graph. And I asked you to locate max points and min points. So it means just I wanted to understand the terminology. It's a very primary school task. When you have the graph, don't lose the logic. The logic is we don't have the graph right now. Yes? We want to find some tools in our hand to be able to draw qualitatively precise graph for the function. Yes? Yes. So this is the logic. Okay, but let us see what is the common property of these local max points and local min points for a function which is a well-behaved function, and that is the only thing that you should be considered in high school. Well-behaved, do you remember what was the word well-behaved? Yes?
No shapes. No sharp points.
No sharp points and? Yes? Continuous. They have to be continuous and without sharp points. Yes? This is the one. It doesn't mean that we don't have functions that are not continuous or they don't contain sharp points. Actually, more advanced functions are like that. And then probably the most famous one that you studied is absolute value of x. Do you remember?
Yeah.
This is the sharp point of the absolute value x. So this is not a very well-behaved function because it contains a sharp point. So I mean that if you want to have very functions of these categories, you really don't need to have advanced mathematics. Already absolute value of x at this point is not well-behaved function. But so this means that in this topic we don't consider it. Yes, we only consider very smooth functions like that. Okay, so now can you tell me, even though this function is max, this point is a max point, this point is a min point, but these two and all other max and min points, local max and min points, have some geometrical property in common. What is that property? Even though one of them is max, one of them is mean, it is completely different in human societies. Having maximum money in your pocket and having minimum money in your pocket is completely different situations. But here, they have the same, they have some common property, yes?
Key value is 0.
The k value.
Yes.
Yes. So it means, so in other words, what he is referring is that if I have a well-behaved function, I do not have those sharp points. So if I have a well-behaved function, it means that I can draw a tangent line. Here, it becomes horizontal, even though this is mean, but if I draw the tangent line here, this is still horizontal. Yes? That is one thing. When I say the tangent is horizontal, it means that its slope is how much?
0.
Its k value is 0 here and 0 there. But there is one subtlety. First of all, so let us say, if I want to find these points, what is a good way to look at the problem? So for example, let us say this number is a, which we don't know. I give you the function. The function is given, sine x, x squared, whatever. And then you want to find this number and that number. If I give you the graph of the function, it is very easy. You put your ruler here, draw this line, you find this. But now you don't have the graph in front of you. You want to calculate them precisely. So what is the first suggestion to see that if this method will work or not? Yes?
You take the prime function, the prime of the function, and then put it equal to 0.
Is that understandable for everyone? Because if I give you the function f of x, do you remember when you calculate f prime at x, it means the slope of the tangent line at the point on the graph whose x coordinate is x. But you want to have this slope to be 0. So this means that you differentiate the function, you get a new function, you find the zeros of the derivative, you get some numbers. Yes? These numbers might be, definitely one of them is this a. Definitely, because if I ask you what is the slope at this point, it is 0. So when I put the derivative equal to 0, definitely one of the numbers that I get is 0. This a. Another number in this picture is what? B. Even if I don't get extra points, still I have some problems. Yes? Assume that I solved this and I got these 2 points. And again, imagine, you do not have graph in front of your eyes. The reason that I put it here is because I want you to understand the connection. But the logic in this chapter is we don't have the graph. So you put the derivative equal to 0, and if this is the scenario, a and b will appear here. Even because if you get some other number here, then you will be a little bit in trouble. But now assume that you don't have any number coming out from this equation. You just get this one and this one, but still you have some problems to be addressed. What problem is that? What problem is that? Yes?
Which is which?
Which is which? Because you don't have the graph. You got a number A, you got a number B. But which one is max, which one is mean, we don't know. Because we don't have the graph yet. This is one problem. Another problem is that I want you to improve your imagination. We had this in chapter 1 before. It might happen that you get some point, some number here, which is not a max nor a mean. This can also happen. Can you imagine how? So let me clean this and make a new scenario here. So can you imagine what might happen that still I get an extra number here without being a max or a min? I can imagine like this. For example, this function goes here, and then let me try. It's hard a little bit to give you a feeling. Okay, so now let me just give you this number. Let me give you this number. Now, do you think in this new picture, another number definitely will be given to you, and that would be C. Yes, this C will also appear, but here D will also appear. Yes, why? Because it's a little bit strange, but this line is a tangent to the graph and horizontal. So what actually doing, I want you to understand, it's not something very strange. You put the derivative equal to 0 and solve it. whatever you get in this new list is just a point at which the tangent is horizontal. It is, this one is not sensitive to your problem. You see, tangent is horizontal, tangent is also horizontal here. And I hope that you agree. Is this a local mix or a max or mean? The answer is no, because it is not a max, because the height is not higher than all the points in its neighborhood. It is higher than the points on the right, but it is lower than the points on the left. So it is not a max. Is it a mean? For the same reason, no, it's not a mean. So it's not a mean, this is not a mean, this is not a max, and the tangent is horizontal. This point is called a terrace point. Yes? Now let us sum this up. You tell me, I give you a function, I differentiate it myself, I do the hard work, I differentiate it, I put it equal to 0, and I solve it, and I get a bunch of numbers here. What are, if I want to describe the properties of all these bunch of numbers in one sentence, how should I say? All of these, regardless of its nature. I put the derivative equal to 0, I might give some numbers in my list. All of them, you can categorize them under one sentence, yes?
They have a k-value of 0?
Yes, the tangent to the graph at these points, yes, are horizontal. Yes? Okay, so you understand. So you see, it's not very, whenever you put the derivative equal to 0 and solve it, you get the numbers so that if you go and intersect your graph at those points and draw tangents, they are horizontal. Okay, but now the problem is actually a little bit harder. The plot thickens a little bit more. So here, this one is a max, is a local max or mean. It's a max. This one is a mean. This one is a max, but this one is neither. Yes? So let us call this one a fake one. It's neither a max or a mean. But now I want you to understand the problem. So the problem is that when I put the derivative equal to 0, which seems a reasonable starting point, I have some problems. I have to fix it. If I can fix it, then I am done. Now I want to ask for you. Let us realize, how should I be able to detect, be careful, if you have the graph in your eye, in front of your eyes, it's a primary school task. Now you don't have the graph. So it means that you really don't know what's going on. So now, how should I differentiate the commonalities between all of them? The tangents are horizontal. That is very good, by the way, because how many candidates we had before? Infinitely many. I narrowed them down to 4 points. Okay, so that's a very big success so far. But now I want to go more. I want to realize the nature of them. Which one is a max, which one is a min, and which one, if any, is a terrace point. This is what we want to learn today. And that's very easy. I don't want you to memorize them because there are many things similar to this, then you get confused. You should visualize something like this in your head to understand it all the time. Okay, to differentiate a max and mean, I need to look at the differences now. So what is the difference between this point and that point, which somehow can help me to recognize the difference? Yes?
So, for the local maximum, if you start going to the left or the right, then...
always the standard method is going to the right.
Okay.
So let us consider this one.
So for the local maximum, if you go to the right, then it will start decreasing. But for the local minimum, if you go to the right, it will start going up.
No, so I think you are confused. So I'm always going to the right. So before reaching to that max, the function is going up or down?
Oh, it's going up.
Well, it's going up, yes? So might be I understood you in a wrong way, but you are probably correct. So when I am getting closer and closer to this one, first I am at this height. When I am getting close to this point from the left side of this point, all the time the graph is actually increasing. Yes, when I am close enough to this point. And then suddenly after that, the height will go down. So it means that here the function goes up, and then immediately after that the function goes down. Yes? And then the property for a mean is completely different. When I am approaching to the minimum point from the left, you see, again, let me just take another, that's the same thing. It's going down, and it comes to a halt, no up and down, and then suddenly change the direction and goes up. Yes? Is that right? So that is the difference. This one, max, on the left, the function is going up. Do you remember the word? The function is increasing. On the right, the function is going down. The terminology is the function is decreasing. But for a min, before that point, the function is decreasing, and suddenly after that, it is increasing. Yes? But now, the terrace point, so it is the terrace point. What is the property of the terrace point? The terrace point is actually behaving the same thing, before and after. So you see here, the function is going down. It doesn't care what's happening. It still goes down. Yes? And that's when usually you buy bitcoins and then it goes down, whatever. Before that you buy, and after that you buy probably. Yes? And then the other one might be you have a terrace point like that. Let me just draw it here for you. You might have a terrace point like this. Yeah, that's not a very good picture, but you understand. But this time it's a terrace point, but it remains increasing all the time. We don't have two types of terrace points. Yes? If you want, you can differentiate them, but we call them a terrace point. Either this happens or that, it doesn't matter, but these things matter. And these are called, another word for them is extreme points. This is, I want you to know. Because many times, something that I say for a max point is also true for a mean point. So I use the terminology extreme means either max or mean, whatever you want. Okay, so extreme points is clear. These are the extreme points. If I want to categorize these two under one word, the word is extreme. And these two are categorized under one word, a terrace point. We don't want usually to appreciate the difference between them, but we want to appreciate the difference between max and mean, even though we have a common terminology for them. Is that clear? So that is actually the topic. This is called, if you want to write it rigorously, this is a theorem that I describe it here. I want you to know the name. The first derivative test. Okay, so how do you do that? So let me write it more formally and then solve some problems. And the problem is extremely simple, by the way. It's not hard, but I want you to understand it yourself. So if you want to find local extreme points and local extreme points of a function, what you do, the first thing is that determine f prime of x. Second stage is to do what? To find the zeros. So let me write. Solve f prime x equals to 0. Let us say, let a, x equals to a is a number that you get. Okay? And then you want to know if this is a max or a mean or a terrace. This you want to know. So what you do something like this. I want you to understand that. You have a sign table which, I don't know, by convention, they put the derivative in the middle row. So they start with the row for x. Sorry, you don't have this. With a row for x. The second one is, by convention, the derivative. And the third one is the function itself. This means that the number that you get there, you put it here. If you get more points, you put all of them here, but you have to pay attention to the order. If you get 1 and you get 2, 1 should come first, 2 should come second. In a range, in increasing order from left to right. Okay? And now, if I ask you what will happen if I feed this number back into my derivative, I hope that you immediately tell me it becomes 0. Why? Because I myself put the derivative equal to 0 and got a. It is clear that if I put a back, I will get 0. But what I get for the function, I have to put a instead of x in the original function. I get a number which I don't know, so let me just write it as f of a. Okay, now the point is that what happens for the behavior of this function before a? Is it going up, and after a is it going down? If that is the case, then this point will be a max point, yes? But how should I know that? Again, derivative will help me to understand that. Derivative already helped me once to detect the horizontal tangent points. But now, can you tell me how can I again use the derivative to understand the behavior of increasing and the behavior of decreasing of a function? Yes?
You can see if the k value is positive or negative.
Yeah, exactly, yes. Because if by accident I am on the increasing part, wherever it is, it doesn't matter, wherever the function is increasing, if I draw a tangent, let us make it a little bit small, you see that you agree that the tangents are of this direction. So slopes are all positive. It might be different from location to location. One of them are steeper, one of them are actually not very steep. But anyway, this k value for the increasing part of the function is positive, and immediately for the increasing part, it doesn't matter where, it is actually it's negative. The k value here is negative. Why? Because if I draw the tangent line is of a line of this direction. So this is positive, this k is negative, and of course this k is 0, as we know. So this means that, as Gustav said, so what I do, I try to understand what is the sign, positiveness or negativeness, of the derivative. There are 4 scenarios, 4 possibilities. Either before the point is positive, after the point becomes negative. So what does it mean? It means that in this part, before a, the function is going up. This is the way that we show the function is increasing. And the derivative at this part is negative. Here the function is decreasing. If this scenario happens, there are 4 possibilities that can happen, then you can conclude that a and f of a is a local maximum. Yes, is that understandable? So if this happens in your table, this situation arises, then you can immediately conclude that a and f of a as a point is a local maximum point. Let me write. And by the way, let me also tell you, I hope that you know that, if I ask you for a local maximum point, point means always x and y coordinates together. I can ask you what is the local maximum. It means that you need to give me the y value. And I can ask you where this occurs, then you have to give me the x value. So appreciate the differences, yes? If I ask you local point, x and y together should be given to me. What is the local minimum? It means that I am interested to the y value. Where the local minimum occurs, you need to refer me to the x value. Okay, but immediately let me not explain so much. Then it might happen that when you draw your table, you have this scenario going on. Yes, you might happen that the function is negative here, the derivative is negative here, positive here, so it goes down here and then immediately it goes up. Then in that case, a and f of a is a local minimum. Yes? And then there are two more possibilities, but of course you understand that in both cases I will face a terrace point. X, f prime of x, f of x, a, 0, f of a, positive, positive, goes up and up, or I might face this scenario, yes? X, a, 0, f of a, negative, negative, f prime of x, f of x. In both cases, a and f of a is a terrace point. Yes? So you see, memorizing these things probably becomes harder because you have more algorithms coming in. I want you to realize, to understand them, because if you understood what's going on, visualizing the picture is really simple, and then you can just quick it up whenever you need it. This table that you see is called the sine table. Yes?
What if you have a graph that doesn't have a local maximum point?
You will see, because you don't have those functions, but yes, we have some of those functions.
But
For
let's say
example,
you have a function that goes down, then goes straight, then goes up again. What would you do in that case?
no, so that's the problem. If it goes really straight,
Yeah.
then it falls into the category of not well-behaved functions, because if a function comes here,
Yeah.
and if it wants to go straight away, then it will generate some sharp points. Otherwise, so by straight I don't understand. So for example, you can come here and then horizontally and then goes up here. Of course, in that part, if you take the derivative, always all these points, the derivative are 0. Then you can call all of them both a local max and a local mean. That's a good question, because if you have a horizontal line, each point you can call it a local mean and a local max simultaneously. Yes? But these extreme cases, you really don't need to be worried about that. But these are good questions that we can ask and address. But it is not, you don't need to be worried about those special cases in this lesson. Yes? Is that clear? Okay, so now let us immediately jump into some practical problems. Yes? Yes. So for example, I would say sketch the graph of the function so let us write it like this: x squared minus 2x plus 1. So you see, I don't say draw, it means that roughly I want you to highlight the main points of the graph, qualitative. So, if you want to do this, you need to locate, as we came to this agreement, we need to locate all possible extreme points and terrace points for this, because if I use them as anchors, then I probably can have a function. I can draw the function qualitatively precise. So the first step is to use the first derivative test. So the first part, I take the derivative, which I intentionally choose it very simple. So it becomes 2x minus 2. Yes, that's the derivative of that function. Step number 2, I equate it to 0 and solve it. Step number 2, y prime equals to 0. I got y prime is this, so I put 2x minus 2 equals to 0, then I get x equals to 1. Can I be sure this is a max point? No. Can I be sure it's a min point? No. Can I be sure it's a terrace point? No. Right now it's a candidate that might be one of them. Yes? It's just a candidate. We don't have anything. Unless I draw the sign table. Okay? So, and the good point here is that I have only one number, so that's exactly very similar to this scenario. I will give you more examples, of course. So what I do, I draw a sign table. X, I put y prime and y here. The only number that I got is 1, so I put it here. If I ask you what will happen if I fit this one into the derivative, of course you can calculate, but you really don't know because you put the derivative equal to 0 and got 1, so it is clear that if you put 1 in the derivative, you get 0. If you want to double check, that's good, that you haven't done any mistakes, but that is, I put 1 here, I get 0. But then this line is y line, is the function. So you don't forget about this, go to your original function and put 1 there. So it becomes 1 squared minus 2 plus 1. Coincidentally, this also becomes 0. Yes? And now you need to see that before this, the derivative is positive or negative. Okay, this is the way that I want you to do that. So here, before 1, I want to go, because I want to answer this one, so I need to care about the derivative. This line is for the derivative. If I choose a number smaller than 1 and put it here, what do I get? A positive number or a negative number?
Positive.
If I put a number smaller than 1.
Negative.
Yes, I get negative. For example, if you're not sure, you just choose a random number smaller than 1. For example, 0.5, and put it here. It becomes 1 minus 2 negative. And then go after 1, a number larger than 1, and put it here. You don't need to calculate. You just need to know, is it positive or negative? What is that? Positive. And then you see that here the derivative is negative. According to that picture in mind, the function should decrease. And then here the function should increase. Let me also tell you this. It is good to write minus infinity to positive infinity here as well. So it means that, by the way, this question can also be asked. They can give you a function and ask you on which interval or intervals the function is decreasing. Yes? So you see that the function is decreasing here. What is this interval? This is smaller than 1. So for example, in those questions, you can answer like this. The function is decreasing on the interval, which interval? X less than or equal to 1. Because on the left-hand side of 1, I see the function is decreasing. And you can say x greater than or equal to 1, the function is increasing. They can also ask you these simpler questions rather than drawing the graph of the function. But I mean that when you draw this sign table, you are also addressing all those sorts of questions. Yes? Okay, now if you want to draw the graph of this function, if you want to sketch the graph, you just set up a coordinate system for yourself and then concentrate on this point. Write it down in your head, 1 and 0. What type of point now you are sure about it? You were not sure about the nature of this candidate. Now you are sure. What is that? It goes down, immediately goes up. So what type of point is that? It's a minimum point, yes? So this is a local minimum. So the first thing that you draw, if you highlight, is this local minimum. And then this is 1 and 0. This is 1 and 0 here. So, and then when this is a local minimum, you know what the graph looks like around it. Because that's a minimum, the graph should look like this. either wider or steeper. But that would be something around that. Yes? And now, that's it. What happens if I go far to the right, the function goes, so what happens, by the way, that is also good to understand. This is a little bit limit process. So what happens if I put a very, very large number for x? Infinity is not a number, it's a behavior of a number. If I choose a very huge number for x and put it for x in the function, what do you expect? What do you expect to get?
Positive?
No, positive now. I mean, is it big or small? If you put very, very big number, you might get confused. I have already talked about that. When it comes to very big numbers, you really can safely ignore about the role of the one. But one of them is getting bigger, the other one is getting a smaller because of negative sign. But do you remember which will win at the end? Yes?
Positive?
The positive one, because it has higher power. So remember, the terms with higher powers always dominate the terms with lower powers. So even though this is also very big, if I put a very big number, this is also very big, but in the competition between these two, the positive infinity will win. Yes? And then if I put a very, very negative number there, what will happen? A very big negative number. What happens? Yes?
It would become positive.
Again, because this becomes positive, even situation is better. Because this becomes a positive huge number, and minus infinity to power 2 is a very huge positive number, so definitely this becomes positive. And this is also confirming, you know, so this will continue. See, am I expecting to have another bump or a trough here? No, because this is the only local max and mean. There is no surprises left for me, you know, because this tells me that this function should go forever like this. If not, if the function is supposed to turn back, I should have another local extreme point, which according to that calculation, this is the only one. So there is no returning back. Of course, this graph is not precise, but for example, if I want to, I can make it a little bit more precise to give exact number here. But usually these are hard things to answer. Qualitatively, by looking at this graph, it is guaranteed for you that you don't need to zoom out, yes, or zoom in. You will not see any surprises. This graph will continue boring like that forever. Yes? That is what I want you to understand and appreciate. This is now completely confirmed using mathematical tools in our hand. Yes? Is that understandable? So it means that, and of course, and GeoGebra knows usually. For example, GeoGebra can draw the graph on this part, giving you the wrong impression that the graph is like this, but it is programmed in a way that cares about extreme points and try to draw the graph around those things that you have interesting things going on. Otherwise, so you just ask the GeoGebra to draw this. Anyway, GeoGebra is choosing one portion. How it comes that it doesn't randomly chooses this portion? It always chooses this kind of portion because it wants to give you the feedback of what is going on. Yes? Okay. If I want to find the exact number here, can you tell me what to do? What is the exact number for this function? Yes?
X is equal to 0.
Yes, so it means that I put x equal to 0 because I want to find the intersection with this. And if I put x equal to 0, this is 1 exactly. This is why if you want to have a better graph, usually you use some extra auxiliary points to help you to draw it a little bit better. But sometimes it is hard. For example, sometimes, usually I would recommend you to put x equals to 0 because putting 0 in the function and calculating is simple. Don't miss this point. But if you want to find the intersection with the x-axis, it is not usually easy. For example, if I have a complicated equation and if I put it 0, I will not be able to solve it. So myself always find this intersection with the y-axis because it is very simple. If it is simple, I will find it with the x-axis. If it's not simple, I ignore that. But I want you to understand, even if I ignore that, even if I didn't know this, but qualitatively I was able to show that this will be a graph. So, by the way, so why do you think this will not happen? So this will go here. Still, we are not done. I want you to understand something. So why do you think this? Because let me do it on the right hand side. It's easier to see. So why do you think the graph will not go like this? Let us see. If I draw the graph like this, it is decreasing on the left. It is consistent with information here. Let us look at the graph of the function on the right hand side. Is this behavior also consistent with increasing?
Yes.
Yes or no?
Yes.
Okay, so it's still I'm in trouble. Yes? So, and then I hope that you agree with me, this is qualitatively different from the one that I did before. If this is the graph, and I am selling this one to you, you should protest, yes? You should complain about that. I want you to know. But this we will not be able to answer until the end of this chapter. This behavior is related to convexity property. So we say that a graph is you see this function is increasing from left to right always. This function is also increasing. But for us human, we realize that there is something different between them. So this is like this, and the other one is like that. We say this graph is convex down, and this graph is convex up. But we will learn how to recognize that property as well without having the graph. But for the time being, don't be concerned about this. Trust me that the graph is this. This will not happen. But I want you to understand, so far it is not enough to have a good qualitative graph right now, because we haven't addressed the convexity property of a graph. Is that understandable? Okay. But so far it's more or less good. Okay, let me give you another example. This is why usually at this part of the book they don't ask you to sketch, because they know that you don't have that property right now. The type of questions that you need to expect to see in the book is not sketching the graph right now, is of this type. They give you a function and they ask you to find the extreme points and determine the nature of them. This is the main question that you need to expect here. So let me give you one example. Determine the local extreme points of the function of the following functions. So let me make this important. So this is important. The following functions and specify the nature of them. What do I mean by this sentence? I mean if it is a max or a min. So let me give you this example. Number one, y equals to, so a third x to the power of 3, and then minus 5 over 2x squared plus 6x minus 1. Yeah. So I think, if you don't mind, let me reorganize these numbers to avoid fractions because it might be confusing for you, but on the other hand, I don't want. So if I multiply by 6, let me multiply everything by 6, because otherwise it would be confusing. I multiply this by 6, it becomes 2x cubed. Multiply this by 6, what was that? Do you remember? It was 5 over 2, it is 15. And then I multiply this by 6, it is 36. I can keep it minus 1 words. Yeah, let me also multiply that by 6. Because otherwise you will be distracted by bad numbers rather than the topic itself. So, this is the problem. I want to determine the extreme points. Do you see? It is not trivial. Do you remember when I was teaching you, because I drew the graph in front of your eyes, you might think it is very obvious, but it is not obvious at all here. Even I really don't know where this, of course I have some experience about third degree polynomials, I have some expectation in my mind, but in principle I don't know what is going on. I have to really calculate. So I don't know how many extreme points I have. Either I have a terrace point or not. I need to discover now. Okay? So the first step, do you remember what was that? To take the derivative, which is a trivial one for you hopefully. It is 6x squared minus 30x plus 36. And then the second step, you put it itself, you put it 0, but you know the reason. Because you are interested in detecting horizontal tangent lines, the points of horizontal tangent lines. If you put it equal to 0, don't get confused here what I'm going to do. If you want to put it equal to 0, you have to solve this problem. And that is a simple quadratic equation. You know how to solve it. How do you solve it? Either PQ formula or ABC. In PQ formula, you have to divide by 6 because you want to make it 1. In ABC formula, you don't have to, but I myself still prefer to divide by 6 because when I divide by 6, I have to work with smaller numbers. Okay? So in ABC formula, you don't have to, but I would prefer to do it. So I divide by 6, and I get this. Now, by the way, let us try to understand. Of course, you can use PQ ABC formula, but you learn how to factorize that, especially for these small numbers. Yes? Can you tell me how to factorize that? Because that would be a faster way. That is up to you, which one you want to do. Yes? So can you tell me, I need two numbers whose sum is this number and the product is this number. If you cannot guess, you just solve it using PQ or ABC formula. What are those numbers?
Negative 2.
Negative 2 and?
Negative 3.
Negative 3. But when you put it equal to 0, what are the x's that I am interested in?
2 and 3.
2 and 3. So x is equal to 2, put it in a box, and x equals to 3, put it in a box. So far, I have two candidates. So is it possible, can you answer this question, is it possible that I have 3 local max and mean for this function? No, because I have at most 2 candidates. It might be the case that I have lower candidates because some of them might be fake, but I cannot have more than 2. At most, I will have 2 local extreme points. Yes?
Why is it positive, negative, and why is it positive 2 and 3 and not negative?
No, because you put it equal to 0, then you find x. Okay. So you need to move. So you put either this one is 0, x minus 2 is 0, so x is positive 2. That's it. Okay. Okay. So now I need to go to a table. By the way, be careful. You don't need to draw 2 tables, one for this, one for that. It's better and it's recommended to draw them in 1 table. Okay? It's really important. Actually, not recommended. You have to do that in that way. Okay. So what I do, I set up my table. Here it's a little bit longer. X and Y prime in the middle by convention. The last one is Y. The numbers that I got, I put them in order on the first row. So it becomes 2 and 3. It is extremely important not write 3 and 2. Okay, if you want to, you can put minus infinity here, positive infinity there, but don't be distracted for these things. You really don't need to do this for this problem. So let me do it like this. Let me clean it for the time being, and then I will add it just for your further knowledge. You really don't need to care about that. Okay, can you tell me what should I write in the middle row below 2? It is 0. If you don't believe, you need to go to the derivative. Don't get confused. You have to go to the derivative and put 2 there and calculate. But this is not necessary, because I myself put the derivative equal to 0 and got these 2 numbers. So it is clear that if I plug them back, I will get 0. So I would recommend you, so unless you want to double check. Otherwise, if you're confident about your calculations, this is 0, 0. But then you need to go in here and here. What do I put here? You see, this is y line. So I have to refer back to my original function and plug 2 here. So you can go to scratch paper, or you can also write the calculations, no matter. So y, if I put 2, it becomes 2 times 2 to the power of 3, 15 times 2 to the power of 2, and 36 times 2 minus 6. So this becomes 16, this becomes minus 60, this becomes 72, and this becomes minus 6. So how much is that? It is 6, no, it is 12 minus 6 is 6, and this is 22, yes? Do you confirm that?
Yes.
So this becomes 22. Yes? And then I have to do the same thing for 3, so I write y of 3 is equal to 2 times 3 to the power of 3 minus 15 times, might be I need your help with your calculator. Yes? So this one is how much? 54. This is 90, 135, and this is 108, and minus 6, yes? And then if you calculate this one, how much is that? Is minus 27, 27, so I think it's 21. Can you just confirm that, please?
Yes.
Yes.
Is it right? Okay. So this is 21. Okay. Now, what was the second? So you see the first row you put it, and then you really don't need to be worried. 0, 0. Here you have to do some calculations. Put these numbers there. Even if it is weak, you can just use your calculator. No worries. But then you need to see, is it positive, or negative in between. And this trick at the level of this word will work for you. So if you want to see, is it positive or negative, this side means this side. It means that lower than 1. Choose a random number which is smaller than 2, the easiest one. I would choose 0. 1 is also working, but 0 is better. And then, don't get confused. There are 2 rows. Be careful that you are not using the wrong rule. You need to refer to the derivative here. Here. Yes? Because this is the derivative row. And put 0, a random number, put it here. You don't need to really calculate that. You have to convince yourself, is it positive or negative? What is that? Positive 36. So it's positive.
Yes.
Between 2 and 3 is the problem. Yes? Unfortunately, 2.5 or whatever you choose, we have to work with fractions. Yes? Okay, so, I don't know. So be careful. Y prime of, I don't know, do you agree with me? 2.5 is at least better?
Yeah.
Between 2 and 3. And then be careful. Don't mess it up. If you put it here, it becomes extremely harder. This one. So what I do, first of all, I can factor a 6 out. So what is left for me? X squared minus 5x plus 6. Do you agree? So I can write the derivative in this form. And then I put 2.5 here. 2.5 to power 2, how much is that? Is 6.25. Plus that 6 is how much? 12.25. And then how much is that? 6.25. 5 times this is 10, 12.5, and then plus 6. Is it positive or negative? You really don't need to calculate. Just this 6 plus that one doesn't reach to this one. So it is negative. So I just want to make sure that, of course you can calculate the exact value, but what matters is the sign, not the exact value. So what is this one? Do you agree it is negative? So this one is negative. Yes?
You have already factored it through.
Yeah. No, because that is not pedagogical. Of course I can use that one as well. But be careful. Sometimes this one is negative. You divide by a negative number. When you divide by a negative number, if you look here, then it would be opposite. Because when you wanted to solve, you might have forgotten that you have divided by a negative number. It means that you exactly get the signs opposite. Yes? But of course, you can always do things faster if you really understand what's going on. Okay, and then from here, I choose a random number after 3. Which one is suitable? 4. Again, I put it in this 4. 4 to power 2 is 16, plus that 6 is 22, but this is just 20, so it is positive. And then this means that the function here is increasing, decreasing, again increasing. So now you immediately realize that there are 2 points involved. One of them is 2 and 22 is 1 point of interest. Another point is 3 and 21. So they are not fake ones actually, they are real ones, but now you need to realize the nature. What type of point is this? What type of point is that? This one is max or min?
Max.
This is max.
Yes.
So it's local max. This point is local min. Sometimes you might say that, okay, this 22 is bigger than this one, so definitely it should be maximum. Yes? Be careful, this picture is not always true, because you might have this scenario, yes? Let me just not waste the board. So you might have this scenario, you see, I might have this, and I might have this. If I ask you this one is a minimum, a local minimum, but this one is a local maximum, but this minimum is higher than this maximum. Yes? So be careful about these things. Don't fall into trap, okay? So now we have a local max and a local min. Let us try, this is not part of this one, but let us try to understand the graph of this function, even though this is not part of this problem. In this section, you need to understand this, and this is finalized here. Yes? But if I want to understand it better, let me change my color, then of course it might be better to put this minus and plus infinities and try to understand the behavior here. If I put a positive infinity to the y, what do you think? Which one will dominate here? The highest power.
Yes.
Forget about them when it comes to power 3. And then if you put a positive huge number in here, you get a positive huge number. So this means that this would be positive infinity. And if I go to negative infinity, again, this will dominate. But x goes to negative infinity, this becomes negative infinity. So if you want to sketch the graph, even though it is not part of this question right now, so what you do, you need to locate the extreme points, 2 and 22. Unfortunately, it's better to rescale them. So let me just write here, it's 2 and 3. So let me consider that this is 21. Okay, I don't know, this is 22, for example. Of course, the scalings are different. Otherwise, it doesn't fit in the rule. Okay, 2 and 22. So 2 is here, and 22 is here. This point is a local maximum. Just draw this for your guidance. Around this point, the graph looks like that. And then 3 and 21 is a local minimum point. So 3 is here, 21 is here. This is a local minimum point. So around this point, the graph looks like that. Yes? And I think you can guess what's going on, yes? So the graph, apparently, they connect to each other. And then, is there any hope for returning back? No, because if it is supposed to return back, you should have another local maximum. So this will continue. This one is also confirming you. You see, on the right-hand side of 3, y continues its journey to infinity, yes? Towards infinity, yes? So it might be it's dying, yes? I don't know. And then this will go up forever, and this will go down forever. So nothing interesting will happen before that and after that. So topologically, this is a phrase. So it means that, so you know that from topological point of view, you can assume that it's a rubber band. And if you don't tear up the rubber band, so the shapes are equivalent. So for example, an ellipse and a circle are the same thing from topological point of view. Because if that's a rubber band, I can just stretch it a little bit to make it an oval, yes? So I mean that the graph of the function that you are drawing is something like this. Of course, if you want to draw it exactly, of course, probably I'm exaggerating the difference between up and down here. It is more realistic. This max and min differ only by 1 unit. But this is the type of the function that you get. Is that understandable? But still, this can go like this, or this part can also go like that, which we haven't addressed the question yet. We will answer it later, but this will not be the case. And I told you that in this lesson, don't get confused with sketching the graph. This one ending here is your duty. Yes? And I want to give, when the lesson finishes?
11:40.
40. So let me see that if I can give you another example, then we will end up the lesson. So let me give another part number 2 to it. Just let me pause the recording a little bit because I don't have. Okay, now we are back actually. So this, you remember the question is still the same question, but we want to talk about this function. I hope that this really works, otherwise it would be a waste of time. Okay, so the first step is as before, yes? I just every question, that is very good by the way. Everything here is algorithmically, you just follow the algorithm. So the first thing that you do, let me change my color here. So you take the derivative, so it is 12x cubed minus 24x squared plus 12x. Agree? Yes. And then you equate it to 0 to find the candidates. So this becomes 12x cubed minus 24x squared plus 12x equals to 0. But you face a little bit of problem here because this is a third degree inequation, and you know that by the experience you got in the first chapter, in principle it is very hard to solve it unless we can factorize it. And remember, always you get some question that you can easily factorize. So what can I do? I can factor what out? 12x, more than x, 12x. Then what will happen? It becomes x squared minus 2x plus 1 equals. The good news is that my cheating worked actually. Okay. So this becomes 0. And then what happens? Even I can factorize this a little bit more. Is it a recognizable pattern for you?
Yes.
What is that? Yes. X minus 1 squared. Yes?
Yes.
And now, even though my derivative is a third degree polynomial, and sometimes third degree polynomials have 3 roots, but here I have only 2. One of them is what? One of them is what? What are my candidates? Can you tell me?
X equals 0.
0 because of that factor, and
1.
1 because of that factor. So these are my candidates. But I haven't determined the nature yet. Okay, so what I do, I set up my table, x, y prime y. Don't be distracted by negative infinity and infinity because you really don't need them here. But I need to keep the order, 0 and 1. Okay? And do I need to check it for derivative? If you trust your calculations so far, you really don't need to recalculate. This turns out to be 0. But for y, I have to calculate. But on which function I have to apply? On the original function. And then the good answer is that, the good news is that it's very simple. If I put 0 here, you really don't even need to calculate with the calculator. It becomes 12. And then I put 1 again in the original function. That's also easy. Then I put 1. I don't need to bother about x. It becomes 3 minus 5 is... So 3 minus 8 minus 5 plus 1 plus 13. Yes? And now, this is the time that I need to have these signs. Choose a random number before 0, but now be careful, you are working for the derivative. Minus 1 is a good choice. Go to your derivative. Here is your derivative. So by the way, you can factorize it in your head. By the way, do you agree this part without being 0 is my derivative, yes?
Yes.
Okay, and now I am choosing minus 1 and put it here. It becomes negative. Because 12 is always positive. X minus 1 squared is always positive. I really don't need to bother about these two parts at all. I need to only be careful about x. If myself choose a negative value for x, the whole combination becomes negative. Yes?
Yes.
And if I choose a number between 0 and 1, it is positive. When I put it here, I hope that you agree it is positive. When I choose a number larger than 1, for example 2, again it becomes positive. Now, this is the spy, yes? This is the fake one. Because you see plus plus, yes? And now what is happening here is going down, but here is going up, and here it's going up. This guy infiltrated in our lesson today. Yes. So we were able to catch it in the last moment. So here, what is what is the nature of this one?
Local minimum.
Local minimum. What is the nature of this one?
Fake.
A fake one, or which in mathematics, a
Terrace.
point. So you see, this is extremely important. So sometimes, I want you to understand that if you just calculate and guarantee that these are extreme points, that it might not be true, yes? Because we were able to detect that. Okay, and I want you to we have 5 minutes, or we can actually do Geogebra demonstration here. I have to record, but I need to change this one for people at home, and then it's very okay, so hopefully the people at home also can see something. But you see, it is an empty, so you cannot see it. Why is that?
The projector.
Yes, what is happening here?
What?
Yes, don't worry about these parts.
Infinity.
Yeah, hopefully it works. Okay, but you see, this is an empty graph now. And the reason is probably clear, because it is out of reach, I think, or no. Yes, it is there. Yes, so you see that is actually very thing. Might you get the feeling that this graph is empty? It was not empty, it was lying there. How should I look for it? Because I knew it from mathematics. And then you see the nature of the terrace point here, you see? This is this number. It's very hard, but of course you can use GeoGebra in the future, but I want you to see, this is a local minimum together with a terrace point. And that was exactly what we confirmed, yes? We got a minimum point and a terrace point. We can elaborate a little bit about this later, but at least I want you to see that the calculation was more or less correct, yes? Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you, people at home.